For hundreds of millions of years, the Earth's surface had been calm, quiet, and still. The world was ruled by microscopic life, tiny, simple cells drifting in endless oceans. They lived, multiplied, and died, feeding a cycle that had lasted for billions of years. The planet was stable, its chemistry balanced, and its skies tinted orange by methane and carbon dioxide. The sun shone weakly through a haze of gases, and the oceans gleamed dark and greenish-black. Volcanoes still erupted across the continents, releasing clouds of sulfuring heat, but the chaos of Earth's birth had faded. Now, the world had settled into a slow rhythm, chemical, steady, predictable. And yet, hidden deep within that quiet rhythm, life was about to change the world forever. Because somewhere, in the shallow waters of ancient seas, a tiny cell had evolved a new way to feed itself, a way that would transform the planet's air, oceans, and destiny. It began, as most revolutions do, with something small, a single cell that learned to capture sunlight. These early microbes were the descendants of simpler anaerobic cells, organisms that didn't need oxygen, and in fact, couldn't survive it. They lived by breaking down chemicals in their environment, feeding on the energy trapped in minerals or organic molecules drifting through the seas. But in certain sunlit waters, some of these cells began to evolve a new trick. They developed pigments capable of absorbing sunlight, and that sunlight, as it turned out, was full of power. Instead of relying on chemical reactions, these microbes learned to use light itself to drive their metabolism. They took in carbon dioxide and water, captured the sun's energy, and used it to build their own food. And in the process, they released something new, something invisible, reactive, and deadly: oxygen. At first, it was just a trace, tiny bubbles forming and vanishing in the shallows. The planet didn't notice. The oceans swallowed most of it, reacting instantly with dissolved iron and other minerals. The sky stayed red and thick, the seas dark and metallic. But the process continued. These light-eating microbes, the first cyanobacteria, multiplied endlessly. Every day, they captured more sunlight. Every second, they released more oxygen. And slowly, over millions of years, the balance began to shift. The ocean, once a cauldron of metals and methane, began to rust. Iron particles floating freely in the water combined with oxygen to form solid oxides, reddish-brown minerals that drifted to the seafloor. Layer by layer, they settled and hardened, leaving behind what we now call banded iron formations, vast geological records of that first great chemical transformation. Each stripe of iron is a fossil of oxygen's arrival. As more oxygen poured into the oceans, the chemistry of the planet began to change. Many ancient forms of life couldn't tolerate it. Oxygen was poison to them. It destroyed their delicate chemistry, corroded their enzymes, and burned their cells from within. For them, this new gas wasn't a gift. It was a death sentence. Yet for others, it was an opportunity. Oxygen carried far more energy than any other chemical on Earth. It could power reactions that were faster, stronger, and more efficient. To the few that could adapt, oxygen wasn't a threat, it was fuel. But before life could truly learn to use it, the Earth itself had to change. Because as oxygen began to build up, it triggered a planetary crisis unlike anything before. In time, the ocean's capacity to absorb oxygen was exhausted. The iron had rusted, the minerals were saturated, and oxygen began to leak into the atmosphere. At first, it vanished as quickly as it formed, reacting with volcanic gases and methane. But cyanobacteria were relentless. They continued to photosynthesize generation after generation, and eventually, oxygen began to win. The methane haze that once blanketed the sky began to fade, and without that thick methane to trap heat, sunlight reflected back into space. The planet began to cool. Clouds thickened, temperatures fell, and glaciers crept across the continents. The world entered one of the first known global ice ages, a frozen chapter, often called the Great Oxidation Event, or, more dramatically, the oxygen catastrophe. To the ancient microbes, it must have felt like the end of the world. Entire ecosystems vanished as oxygen levels rose and temperatures plummeted. The anaerobic organisms that had ruled Earth for billions of years either retreated into oxygen-free refuges or died out completely. Volcanic activity tried to reverse the chill, pumping greenhouse gases back into the atmosphere, but for millions of years, ice held the planet in its grip. And yet, as always, life found a way to endure. In cracks beneath the ice, near volcanic vents, and in oxygen-poor sediments, survivors persisted. And among them were the descendants of those same cyanobacteria, the architects of this frozen world. They had remade the planet without meaning to, and now they would live in the world they had created. For millions of years, this balance continued. Photosynthesis filled the skies with oxygen while the Earth's geology and climate slowly adjusted. Glaciers advanced and retreated, continents shifted, and the atmosphere stabilized. When the ice finally melted, the planet that emerged was not the same. The oceans were clearer, bluer, and oxygen-rich. The skies, once orange, were turning blue, and the air, for the first time in history, could support fire. The Great Oxidation Event had ended the ancient world and birthed a new one. It had cleansed the atmosphere, transformed the chemistry of the oceans, and set the stage for a new era of evolution. The age of oxygen had begun, but the story was far from over. Oxygen was both creation and destruction, a force that could breathe life into cells or burn them to ash. And as life adapted to it, the rules of evolution began to change forever. The rise of oxygen was silent, invisible, and merciless. It spread like an unseen tide, creeping into every corner of the oceans, every pore of the seafloor, every layer of the atmosphere. It had no will, no intention, no sound, yet it changed everything. For the first time, the very chemistry of life came under siege. Oxygen, reactive and unstable, attacked the fragile molecules that had once powered the world. It tore apart proteins, dissolved membranes, and burned organic matter with a ferocity that no organism had ever faced. To most life on Earth, oxygen was a toxin, and the more it spread, the more species vanished. Before oxygen, the Earth had been a world of balance, a planet of methane, carbon dioxide, ammonia, and hydrogen. Those gases formed the foundation of life's chemistry, supporting organisms that thrived in warmth and simplicity. But oxygen broke that balance. It consumed methane, one of the planet's most important greenhouse gases, and stripped it from the atmosphere. Without methane's warming power, the sun's light reflected off the surface and the planet began to freeze. This chain reaction turned the world into something almost unrecognizable. The seas turned cold, glaciers advanced, and temperatures dropped globally. It was as if life had pulled the trigger on its own extinction. Scientists call this the oxygen catastrophe, but it was more than a single event. It was a slow, suffocating transformation that took millions of years to unfold. Oxygen poisoned the air, froze the seas, and suffocated ancient ecosystems. The shallow waters that had once been warm nurseries of life became chemical traps. The iron that once kept the oceans red and metallic now settled as rust on the seafloor. Volcanoes spewed gases into the air, but even they could not outmatch the relentless photosynthesis of cyanobacteria. The Earth was trapped in a feedback loop. The more oxygen the bacteria produced, the colder and harsher the planet became. For billions of years, the Earth had been governed by chemistry alone. Now, for the first time, life itself was changing the rules of the game. But in the darkness beneath the frozen seas, evolution did not stop. It adapted. And in that adaptation lay the seeds of something new, a way to survive oxygen and even use it. Some microorganisms discovered that instead of fleeing from oxygen, they could harness its power. They evolved enzymes that neutralized oxygen's destructive effects, turning it into something they could control. Then, step by step, they began to use oxygen to extract energy. This was the dawn of aerobic respiration, one of the most important evolutionary leaps in history. Where ancient anaerobic cells could extract only a small amount of energy from food, Aerobic organisms could unleash more than 10 times as much. It was like upgrading from a flickering candle to a raging furnace. The cost was high. Oxygen could still kill them if not handled carefully, but the reward was extraordinary. With it, life became faster, stronger, and more dynamic. It could grow larger, move more efficiently, and evolve more complexity. This new form of metabolism was so powerful that it would one day fuel everything from insects to whales, from the smallest bacteria to the largest dinosaurs. But in this early age, it was still new, fragile, and rare. Only a few lineages had cracked the code, while the rest of life retreated into oxygen-free pockets of the planet. During this time, the planet's surface became a battlefield of extremes. Frozen continents reflected sunlight into space, deepening the chill. The air grew thinner, the seas more acidic, and volcanic eruptions painted the skies red with ash and sulfur. Yet the cyanobacteria kept going. In shallow seas and under thin layers of ice, they continued to photosynthesize, endlessly releasing more oxygen into the world. They didn't plan it, they didn't know, they simply followed the logic of survival, as all life does. And in doing so, they became the greatest engineers the Earth had ever seen. They reshaped the atmosphere, paved the way for complex metabolism, and created the very foundation for the biosphere that would follow. Over time, the balance began to shift once again. Volcanic activity returned carbon dioxide to the atmosphere, slowly warming the planet. The ice began to melt, the oceans thawed, and new ecosystems emerged in the wake of the catastrophe. This was Earth's recovery, but it was not a return to the old world. The methane haze was gone, replaced by an atmosphere rich in nitrogen and oxygen. The skies, once rusty orange, were now a deep, endless blue. The planet sparkled with sunlight. The new Earth was colder, brighter, and far more dynamic than the one that came before. It was a planet ready for something more. But this recovery came with consequences. The rise of oxygen had permanently changed the chemistry of the atmosphere and oceans. The once stable methane cycle was gone, replaced by oxygen-driven weathering and carbon exchange. Lightning sparked new chemical reactions, producing nitrates and other compounds that fed evolution. Storms grew more intense, the seas more nutrient-rich. Every element of the planet, air, water, rock, and life, had been rewritten by oxygen. And this new oxidized Earth opened the door to something entirely new: complexity. The groundwork was now set for the next great leap, the evolution of multicellular life. But before that could happen, oxygen had one more role to play. It had to transform not just the chemistry of the planet, but the biology of its inhabitants. The Earth was still scarred from its frozen past. Glaciers had carved the continents, leaving behind valleys and plains that stretched beneath new oceans. When the ice melted, rivers of minerals poured into the seas, filling them with nutrients, iron, phosphorus, and sulfur, all washed from the land. And in that nutrient-rich water, life began to bloom again. But the world that emerged from the oxygen catastrophe was not the same. The rules of survival had changed. Oxygen, once a deadly poison, was now a permanent feature of the atmosphere. To thrive, life had to evolve or disappear. At first, the survivors were simple. Tiny microbes that had adapted to tolerate oxygen began to dominate the oceans. Some hid inside protective layers. Others evolved enzymes to neutralize oxygen's damage. But a few, a rare and extraordinary few, did something even more remarkable. They didn't just tolerate oxygen, they used it. Through countless mutations, these organisms developed the machinery to harvest oxygen's power safely. They evolved specialized proteins, like cytochromes, that could control the flow of electrons through their cells, turning oxygen from a corrosive gas into a reliable energy source. This was the foundation of aerobic respiration, the process that would one day power every heartbeat, every breath, every movement of every complex creature to come. The survivors of the oxygen catastrophe were not just clinging to life. They were building the blueprint for the future. Over time, The descendants of these aerobic microbes diversified into new forms. Some remained free-floating in the oceans, drifting in clouds of plankton. Others began to form colonies, loose associations of cells that worked together for mutual benefit. At first, these colonies were simple, clusters that shared nutrients or protection. But in time, cooperation became more efficient than isolation. Nature began to experiment with organization. Certain cells specialized in capturing food. Others focused on movement or protection or reproduction. And although these early groupings were still primitive, they represented a turning point, a step toward multicellularity. For the first time in history, life was beginning to act not just as individual cells, but as coordinated units. It was a small hint of what was coming, the rise of complex life. Meanwhile, the Earth itself was transforming. The atmosphere was thick with nitrogen and oxygen, and the ozone layer, formed from oxygen molecules reacting with sunlight, began to take shape high above the planet. That thin shield of gas would prove vital, blocking harmful ultraviolet radiation from the sun. It was one of the most important side effects of the oxygen revolution. Without ozone, complex life on land would never have been possible. The oceans, too, were changing. Oxygen penetrated deeper into the water, creating new habitats. Regions that were once toxic and anoxic began to support thriving ecosystems. Microbial mats, stromatolites, and planktonic colonies covered the shallow seafloors. From space, Earth no longer looked like a dull, rust-colored world. It shimmered blue and white, a planet alive with chemistry and light. Deep in the oceans, new forms of metabolism were evolving. Some microbes began to feed not only on sunlight, but on each other. The rise of oxygen had opened the door to a new kind of energy, one based on consumption, not just photosynthesis. Cells learned to engulf smaller cells, digesting them for nutrients. Predation had entered the story of life. It was brutal, but it drove innovation. As predators evolved, so did prey. Membranes grew thicker, movement became faster, and internal structures became more complex. Every adaptation triggered another, and the arms race of evolution began to accelerate. It was in this crucible of oxygen, predation, and cooperation that the first truly complex cells would emerge. But before that leap, something else remarkable happened: a partnership. At some point, a large cell engulfed a smaller one. Instead of digesting it, the two began to coexist. The smaller cell was an aerobic bacterium, perfectly adapted to handle oxygen. It produced energy far more efficiently than its host could on its own. The host provided protection. The symbiont provided power. Over countless generations, they became inseparable. That partnership gave rise to the first eukaryotic cells, the ancestors of all complex life on Earth. These eukaryotes were unlike anything before them. They had nuclei to store DNA, mitochondria to generate energy, and internal compartments to organize their chemistry. They were larger, more flexible, and more adaptable than any prokaryote before them. And because of oxygen, they could afford the luxury of complexity. Where their ancestors had been limited by low energy yields, eukaryotes had abundance. They could grow larger, evolve more specialized structures, and sustain more intricate internal systems. It was a revolution within the revolution, a new kind of life, powered by oxygen and built for diversity. The oceans of this new world glittered with microscopic diversity. Single-celled eukaryotes swam through sunlit waters, hunting and reproducing in ways their ancestors never could. Some evolved flagella, whip-like tails for swimming. Others developed shells or spines for protection. Their internal complexity gave them an edge in every environment, and evolution flourished at a pace never seen before. The Earth was alive in a new way. The microbial world was no longer simple or uniform. It was dynamic, competitive, and creative. And as oxygen levels continued to rise, the potential for even greater complexity loomed just beyond the horizon. The partnership between host and symbiont, between the early eukaryotes and their mitochondria, became the most successful alliance in the history of life. It allowed organisms to use oxygen as an inexhaustible power source. driving energy production at levels unimaginable to their ancestors. Every breath of oxygen on Earth today is a direct inheritance from that event. Over the next hundreds of millions of years, eukaryotes diversified into countless forms. Some remained single-celled, but others began to gather in colonies again, only this time with far greater coordination. Each cell in these colonies was now a powerhouse, capable of producing its own energy and contributing to the whole. Slowly, individuality began to blur, and collective living became evolution's next grand experiment. The oceans shimmered under a pale blue sky, alive with invisible motion. Billions of cells drifted through the water, multiplying, feeding, and evolving. But somewhere among them, something extraordinary was taking shape. Cells were beginning to organize, not just by accident, but by design. This was the dawn of complex life, a transformation made possible by oxygen. Eukaryotic cells, with their energy-rich mitochondria and elaborate internal structures, were the architects of this new era. Unlike their simpler bacterial ancestors, they could grow larger, divide more slowly, and build specialized parts. They could afford to experiment with shape, function, and behavior. Oxygen had unlocked a new world of possibilities, and evolution began to explore them all. In some corners of the ocean, colonies of eukaryotic cells grew into sheets and filaments, sticking together after division instead of drifting apart. Over time, these clusters became more sophisticated. Cells on the outside absorbed sunlight or nutrients, while those inside were protected and could specialize in reproduction. This was cooperation turned into structure, the foundation of multicellularity. At first, these organisms were still microscopic, soft-bodied and simple, but in the grand sweep of time, even the smallest innovations could transform the world. Each step built upon the last: new shapes, new metabolisms, new survival strategies. The ocean was a living laboratory, and oxygen was its catalyst. With every passing million years, evolution learned new tricks. Cells began to communicate using chemical signals. They learned to coordinate, to divide tasks, to form tissues. The boundaries between individuals blurred as cells started acting as parts of a larger whole. Life was no longer just single cells adapting to survive. It was becoming organisms designed to thrive. Meanwhile, oxygen continued to reshape the planet's chemistry. Weathering of rocks released new minerals into the oceans, feeding further biological growth. The ozone layer strengthened, shielding the surface from ultraviolet radiation. The global temperature stabilized as the carbon cycle adjusted to the presence of free oxygen. The Earth was, at last, entering a kind of balance, a world not too hot, not too cold, filled with stable oxygen and teeming with potential. It was the perfect cradle for evolution's next leap. By around 1.8 billion years ago, eukaryotes had spread across the globe. They were still simple by modern standards, but the groundwork for complexity was complete. Life was no longer limited by energy. It was limited only by imagination. Some eukaryotes began forming multicellular colonies with clear differentiation. These early multicellular forms resembled algae or simple proto-animals floating through shallow seas. They didn't have organs or skeletons, but they were organized enough to respond collectively to light, temperature, and food sources. They were the prototypes of everything to come: plants, fungi, animals. At the same time, oxygen levels continued to rise, albeit slowly. For hundreds of millions of years, the Earth's atmosphere hovered in balance. Just enough oxygen to support complexity, but not yet enough to ignite full biological expansion. It was a long, quiet interlude, a slow build-up to the next explosion of diversity. During this period, sometimes called the boring billion, evolution seemed to crawl. Continents drifted lazily, the oceans were calm, and the atmosphere changed little. But beneath that apparent stillness, life was preparing its next masterpiece: oxygen, energy, and organization. These were the ingredients evolution needed to create the complex ecosystems of the future. Inside these early multicellular organisms, cells began to specialize even further. Some took on structural roles, forming protective layers or supportive tissues. Others became sensors capable of responding to light or chemical gradients. Still others handled reproduction, ensuring the continuation of the lineage. This division of labor was evolution's first great act of engineering, turning individual survival into collective strength. It was an innovation so powerful that it would echo through every complex life form to come. The oceans of this new era were strange and beautiful. Vast mats of microbial life still covered the seafloor, but now, delicate filaments and blobs of multicellular organisms drifted above them. Many were translucent, their bodies glowing faintly as sunlight filtered through the waves. Predators and prey existed in miniature, microscopic hunters chasing smaller cells, engulfing them in flashes of energy. It was a silent world, without eyes or sound, but full of interaction and tension. Every movement, every division, every mutation was shaping the story of life, inch by inch. And all of it, every heartbeat of evolution, was powered by oxygen. Oxygen had done more than reshape the chemistry of the Earth. It had rewritten evolution's playbook. For the first time, energy was abundant enough to support structure, coordination, and growth. Organisms could now afford complexity. They could build bodies instead of merely existing as cells. This new abundance marked the end of the planet's microbial monopoly. The simple world that had persisted for over 2 billion years was fading. The age of microscopic dominance was giving way to something grander, a world of tissues, organs, and ecosystems. Around 1.2 billion years ago, evidence suggests the first multicellular red algae appeared. These early plants were small, but they marked a turning point. Photosynthetic eukaryotes were now building bodies of their own. Soon, green algae followed, spreading through the sunlit shallows. They too relied on oxygen, not just to breathe, but to protect themselves from ultraviolet light through their pigments and metabolic processes. These simple multicellular plants formed the base of new food chains, supporting other organisms in a growing web of life. The Earth's biosphere was no longer a thin film of microbes. It was deep, interconnected, and self-sustaining. As oxygen levels slowly rose, another effect began to emerge, the possibility of large size. In a low-oxygen world, size was limited by diffusion. Cells could only get oxygen by direct contact with their surroundings. But as oxygen became more plentiful, larger bodies could support themselves. Internal transport systems powered by oxygen became viable. This change would eventually make complex organs possible: hearts, lungs, circulatory systems. But for now, it meant that life could finally grow beyond the microscopic. And that was the beginning of something profound. The stage was now fully set. Earth's atmosphere was stable, its oceans rich in oxygen and nutrients, and its living inhabitants more complex than ever before. The Great Oxidation Event had transformed the planet, paving the way for complexity. The experiments of evolution during the so-called boring billion were about to bear fruit. The next chapter of life's story would not be slow nor quiet. It would be sudden, explosive, and dazzling. The world was ready for its first great burst of visible life. The world was alive, quietly, steadily, and invisibly. For billions of years, life had existed in shadow, hidden beneath the waves, written only in the chemistry of the planet and the rocks beneath it. But now, in the twilight of the proterozoic eon, the silence was breaking. Oxygen had done its work. It had sculpted the atmosphere, cleansed the oceans, and given evolution the tools it needed to create the extraordinary. The planet was ready to awaken. By around 800 million years ago, oxygen levels had reached a new threshold. No longer just a trace gas, it now made up several percent of the atmosphere, enough to sustain large, active organisms. It was a slow accumulation, but its effects were profound. This increase in oxygen wasn't constant or steady. It pulsed, rose, and fell with the rhythms of the Earth, driven by tectonics, ice ages, and biological feedback loops. Each burst of oxygen transformed the planet a little more, pushing life closer to the edge of complexity. And somewhere in that shifting balance, the first true animals emerged. They were soft-bodied and simple, nothing like the creatures that would one day crawl, swim, and fly across the planet. They had no bones, no shells, and no eyes, but they were organized, multicellular, and coordinated. They could move, sense their environment, and feed. They were the first metazoans, the ancestors of all animals. The earliest fossils of these beings appear in the record as faint impressions in ancient sediments, delicate patterns that mark where soft bodies once rested on the seafloor. They belong to creatures like sponges and cnidarians, the distant kin of modern jellyfish. They filtered nutrients from the water and lived anchored to the seabed, thriving in oxygen-rich shallows. For the first time in history, the world had animals. But oxygen did more than make animals possible. It made movement, metabolism, and even thought possible. In an anoxic world, energy was too scarce for anything beyond the simplest reactions. But with oxygen, cells could power complex systems, nervous tissue, muscles, circulation. The ability to use oxygen efficiently became evolution's greatest advantage. It gave rise to the potential for behavior, for sensing, for motion. The earliest animals weren't intelligent, but their very existence marked the beginning of something new: active life. The oceans of this time were still strange and alien. The continents had begun to cluster together into a supercontinent called Rodinia, altering global currents and climate. Ice sheets expanded across much of the planet in what may have been another global glaciation. The Snowball Earth events of the late Proterozoic. For tens of millions of years, the planet swung between frozen extremes and greenhouse thaws. Each cycle buried and released nutrients, driving waves of oxygenation through the atmosphere and seas. And with each pulse, life responded. After every freeze, new forms appeared, more diverse, more complex, more energetic. It was as if the planet itself was breathing, preparing for the next great transformation. Around 600 million years ago, the first complex multicellular animals began to flourish in earnest. These were the members of the ediacaran biota, a mysterious and diverse group that would dominate the seas for tens of millions of years. They were soft, often leaf-like or disc-shaped, and many had fractal patterns branching through their bodies. Some floated freely, others lay motionless on the seafloor, absorbing nutrients directly through their skin. A few may have moved slowly, gliding across microbial mats. Though alien in appearance, these were our earliest macroscopic ancestors, the first truly visible life forms. They mark the beginning of biological complexity on a planetary scale. The ediacaran seas were unlike anything that came before. For the first time, ecosystems existed, communities of organisms interacting, competing, and coexisting. Oxygen levels were high enough to support predators, grazers, and scavengers. Energy flowed from sunlight to microbes, to algae, to animals. The web of life was forming, and with it came new evolutionary pressures. Predation appeared, one of the most powerful forces evolution had ever unleashed. It drove defense, armor, speed, and intelligence. For every organism that evolved to hunt, another evolved to hide or flee. This dynamic arms race would soon change everything again. By 560 million years ago, the ediacaran world was fading. Some of its creatures vanished mysteriously, leaving only faint fossil traces. Others may have evolved into new forms that would populate the next era. Either way, the stage was almost set for the event that would forever change the face of the planet. The Cambrian explosion. The buildup of oxygen, the rise of multicellularity, the emergence of predation and mobility, all were the prelude. Every innovation of the oxygen revolution had been a step toward this threshold. The Earth had spent billions of years preparing for an explosion of diversity that would redefine life itself. As the Cambrian dawn approached, the seas were ready, rich in oxygen, nutrients, and evolutionary potential. Genetic complexity was high, the ozone layer strong, and ecosystems diverse. All the conditions were aligned for a creative detonation of evolution. In just a few tens of millions of years, life would burst into a spectacular variety of forms: shells, limbs, eyes, and minds. But that story belongs to the next chapter. For now, the oxygen revolution had reached its culmination. It had taken a barren, toxic, lifeless world and turned it into one filled with movement, light, and possibility. It was the greatest planetary transformation in history, the first breath of a living world. Oxygen had rewritten the story of Earth. It had turned poison into power, chaos into balance, simplicity into complexity. And though it had caused mass extinction and frozen the planet, it also laid the foundation for everything that followed. Every creature that would ever breathe, every fish, bird, mammal, and human owed its existence to that ancient revolution, to the cyanobacteria that filled the sky with air, to the cells that learned to use it, and to the planet that survived the transformation.